Hello everyone, and in this video I'm going to demonstrate internal force calculation of the material. Okay, and this example is much easier than the first one. I think the first one is the most difficult. Okay, so the second one is easy. Okay. And the second one is that here is that there's a rod hanging over there, and there's a support. There's a support of this rod, and this rod there is the engine. Engine tell you is 500 kilogram engine suspended from the crane boom in big in this figure. Okay, this device this picture tells you a lot of information. Okay, and yeah, you want to calculate it. Want to calculate internal force from the section E. From the section E. Okay, so for this type of question, first of all, we just draw the free body diagram, and then we decide to cut the section using cut section method. Okay, and the cut section method. Okay, I think I choose to calculate from the right, not from the left. Okay, because actually this problem didn't tell you, but it should tell you here is a pin support. Okay, piece of pin support. Okay, I choose from calculate from the right because like I said, if you do this cut, you can ignore everything from the left, so you don't have to care about the support reaction from the A. Okay, and here is a CD here. Okay, is a FCD here. FCD here. Okay, and the section E, yeah, we assume there is a normal force, shear force, and moment at E. Okay, and the engine here is it's 500 kilogram. Mm-hmm. 500 kilogram, but actually it's a mass, it's not a force. So if a mass will transfer to force is times 9.8, so that's a force. Okay, so you've cut a section here. Okay, use the EB section to do the calculation. Okay, so and then if you have to do a force balance to get the VE, NE, and ME. Okay, VE, NE, and ME. Okay, but the problem is we only know the force at the B. Okay, the problem didn't give you the information of force CD. Okay, force CD we don't know. Okay, so if you want to solve the internal force on the cross section E, you have to figure out what is force CD, or you cannot do anything. And how to calculate the force CD? Yes, you have to do the global rigid body equilibrium. Okay, global rigid body equilibrium. Body. And if you do the global rigid body equilibrium, okay, it's very sad. You still have to consider the support reaction. Okay, so global rigid body equilibrium. First of all, we just draw the free body diagram. Okay, free body diagram here, and here is B. Okay, free body diagram 500 times 9.8, and the CD is here. So here's C, here the C is here, and the CD is here for CD. And I just assume it's theta. And yeah, yeah. We intentionally use the EB section to do a calculation. We think we don't have to calculate the support reaction, but after all, in the whole global rigid body equilibrium, you still have to consider the support reaction from A. And because it's a pin support, so we know how the reaction force. Okay, XAX and AY. Okay, so and let's start with the okay. Don't forget the goal is to find what is CD. Okay, so we have to list all the equation, but we don't know which equation is going to be used for. But so we have to list all of them. Yeah, that's very sad. Um, so for the global rigid body equilibrium. Which reference point we want? I think we choose, okay, we choose A as a reference point. Okay. Okay, for the, okay, fx is equal my fx equal to 0. Okay, ax and, okay, do we have other x component force? Yes, we have fcd times cosine theta. FCD times cosine theta, but be careful, it's a reverse, it's point to the left, point to the left. So it's the negative sign minus FCD cosine theta. Okay, and then done equal to 0. Okay, that's the first one. But cosine theta, we know the cosine theta, we know the cosine theta, we know cosine theta. Okay, because theta is here, so it's 2. It's okay. Here's 2. Here's 1.5. So actually, it's 3, 4, 5. Okay. So cosine theta actually is 0.8. But even if we know the cosine theta, okay, we still cannot solve FCD. Okay. So. Mhm. So this equation is not really useful. Okay, the next one is ay okay, times FCD. If we know the sine theta, FCD sine theta, it will point up, so it's positive. And don't forget a y component, we have a minus here, minus 500 times 9.8 equal to 0. Yeah, we know the sine theta. Sine theta is 3 over 5, but this equation still cannot let us to calculate the FCD. Okay, so the next one, that should be this one. Okay, F, sigma MA equal to 0. If you A at reference point, yeah, X, A, Y, we don't have to consider the moment created by X and Y because it's acting at this state point, so we don't have to calculate the moment. But FCD, we have to consider that FCD and only the sine theta create a moment. Okay, sine theta create a moment, and the FCD sine theta is point up. Its point up, reference point is A, so it will create a counterclockwise rotation. And so it's positive. Its labor arm is 1 plus 1, so it's 2. Okay, and it's positive, and also and the force at the B will also create a clockwise rotation. Create a clockwise rotation, so it's a become a negative, and its labor arm is 1 plus 1 plus 1 is 3, so it's minus 500 times 9.8 times 3, and it's equal to 0. Okay, so sine theta we know it. Sine theta is 3 over 2, 3. Oh, sorry, 3 over 5. So okay, what is FCD? Let's see. Okay, 500 times 9.8 times 3 divided by 2 and times 100 by 3. So 12250. Mm-hmm. 12250. Mm-hmm. Okay. Okay. FCD is 12250. Okay. And so Newton. Okay. Okay, so we got FCD. Okay, we got this information, and then we can go use FCD, go back to the free body diagram and the CD, sorry, at the EB section to calculate VE, ME, and NE. Okay, so it's a free body equilibrium again. Okay, so, okay, let's start from F sigma Fx equal to 0. Okay, so x equal to 0, x component force is Ne, is pointing to the left, so point to the left minus Ne. And okay, don't forget we have FCD have x component, it's also pointing to the left, so it's negative, so it's FCD times cosine theta equal to 0. Okay, anything else? X component, no. Okay, so NE is equal to minus FCD times cosine theta. So cosine theta, what is cosine theta? Cosine theta is 0.8. Cosine theta is 4 over 5. So let's calculate 12250 times 0.5. So it's 900 900 Newton. Okay. Yeah. Mm-hmm. Mm-hmm. Yeah. Okay. Did I calculate this correct? Let me see. Okay. Fine. Let me check this again. Okay. 500 times 9.8. Okay. Times 3. Sorry. Two 12262. Okay, I think if we're more accurate, it should be 12262.5. 12262.5. Because if we choose 9.81, yeah, 9.81 or 9.81. Okay, so okay, let me calculate this again. So okay, mhm. 12262.5 times 4 divided by 5. 9810. Yeah, that's true. Minus 9810 Newton. Okay, that's NE. Okay, so sigma Fy equal to 0. What do we have? Okay, MVE point up. Okay, and FCD sine theta also point out, so it's plus. FCD sine theta, and we have the weight at the B point down. So okay, it's 9.81. Okay, minus 500 times 9.81 equal to 0. So okay, so what is VE? So let's use a calculator again. 500 times 9.81 minus 8 2.5 times sine theta. Sine theta is 0.6. So it will be minus 2452.5 Newton. Okay, so actually the answer is 2.45 kilonewton. Okay, yeah, the same answer. Okay, finally, what is ME? Okay, ME. Okay, we choose the E as a reference point. Okay, so in order to finish this calculation, I have to, okay, get this off. Okay, okay. Mhm, okay. Okay, for we use E as a reference point, summation ME equal to 0. So at this point, at E this point, we have the moment. We still have to write it out. Okay, the moment, okay, whatever moment do we have? FCD, okay, FCD sine theta, right? FCD times sine theta. Okay, and reference point is E, so it will create a counterclockwise rotation. So it's positive. And here, the B, force B here, it will create a clockwise rotation. So it will become negative. So it's minus 500 times 9.1. Don't forget lever arm, lever between E and B, lever arm is 2. Be careful. B and E, this lever arm between B and E here is 2. Okay, here is lever arm is 1. Yeah, I forgot the 1 here. Okay, so why so messy here? Okay, so we have to times 1 here. I forgot to times 1 here. I forgot to times the lever arm, but we should write it out. Okay, so the total moment at E it must be 0 because the whole system at that rich body equilibrium. Okay, so sine theta is okay. It's about 0.6. Okay, FCD we know. So what's the ME? Okay, let's use our calculator. 62.5 times 0.6 and minus 500 times 9.81 times 2. And go to over there. Okay, really? Do we really have the same answer? 62.5 times sine theta times sine theta times sine theta. Sine theta is minus 500 times 9.81 times 2. Oh, sorry, say, sorry. Uh, 2? Yes, 2. Mm-hmm. Fine, 2. Okay, so ME is, okay. So finally, ME is 2452.5. And that's Newton times the meter. Yeah, we got the positive moment at E because we assume it's positive at the beginning. And you see here, the textbook show the answer is minus 2.45 kilonewton times meter. I believe this is because in the textbook, at the beginning, it assumes it's clockwise. At the beginning, it assumes it's clockwise. And then he get the negative answer. That means the real answer is counterclockwise. And here we assume it's counterclockwise. Okay, so we get a positive, so that's why it's the real answer is counterclockwise. Okay, textbook because initially it's assumed it's clockwise, and then you get negative answer, so the real answer is still counterclockwise. Okay, let me check the textbook. I think just what I say. Okay, 7.2. Okay, very hard, very heavy textbook. 7.2. 7.2. Here. 7.2. Okay. Hmm. Okay. That's my fault. Okay. The reason for the textbook to get a negative sign because it's calculated from the left, not from the right. Yeah, the textbook. I'm not sure how to show you this. Yeah, the textbook. There's no. Ah, yeah. too high. That's two. Okay, that's two. Okay, so that's two. Yeah, you cannot see it. Okay, the reason for textbook get a negative answer because it's calculated from the left. Okay, but we calculate from the right, so we have negative sign. Okay, so that doesn't mean we do calculation wrong because we calculate from the right and calculate from the left. You have the reverse answer. Okay, we have reverse sign. Okay, so I should make a note here. Calculate from the left. Okay, calculate from the left. Okay, but the calculate from the left, we should have the reverse sign of the shear force. Why? But we still have the same sign on shear force. Where goes wrong? If we calculate from the left, we should have the reverse sign on shear force, but we still got the same sign on shear force. That's very annoying. Let me see. Shear force point up. Shear force point up, point up. Point down. Let me check my shear force. Okay. Sine theta. Mhm. Sine theta. Yeah, the shear force we still got a negative there. Okay. I just start the video here. I'll figure that out. Okay. See you next video. Bye bye. Okay, I'll figure that out. The shear force issue.